The voice model is smaller than a typical smartphone photo bus. The Nano version is just 15.97 megabytes. The larger Micro model is 37.53. Yet text goes in, a complete 24 kilowatts waveform comes out, and this run is happening inside the browser with no hosted inference queue. The Nano version is just 15.97 megabytes. The larger Micro model is 37.53.
Hello there, this is a browser test. Dr. Smith paid $42.50 at 3:15 p.m. on June 24, 2026 for order I-2093. This version chunks longer text into sentence-sized pieces and streams playback, predicting each chunk's synthesis speed from the one before it.
That sounds impressive for 16 megabytes, but tiny doesn't automatically mean useful and local doesn't always mean fully offline. So I am going to test the complete claim, run both models, inspect the architecture and give the Inflect the kind of text that usually breaks small speech systems. First, complete means the parameter count includes the synthesis path all the way to audio. No external neural vocoder hiding off screen. Second, offline means the model can generate after its files are downloaded without sending our text to hosted API. Third, speed has to be faster than playback on ordinary CPU class hardware. And fourth, the voice has to survive more than a friendly demo sentence. I am testing Nano for footprint and Micro for quality. I am also keeping the limitations visible because this is one fixed English voice, not a miniature replacement for every voice platform. Inflect V2 landed with exactly kind of claim the local AI community loves. Two complete models under 4 million and 10 million parameters. The author, own song, says Nano is one of the smallest neural TTS systems he knows that still produces unusable speech. The Reddit discussion is immediately moved past novelty. People ask about Android, Home Assistant, C++ images, browsers deployment and multilingual training. The community isn't asking whether a 16 megabyte model is cute. They are asking where it is. One developer even put the phonics version into the browser using WebGPU with a CPU fallback. That is the real opportunity here. Speech generation in apps where cloud round trip a large model or a recurring API build makes no sense. The author also compares Nano parameters count with Kokoro, Chatterbox and Fish Audio. Treat that as a footprint context, not a quality ranking. Those systems have different voices, architecture, datasets and features. Inflect is not claiming that one fixed 4 million parameter voice replaces a multi-speaker or multi-billion parameter platform. The investigation is narrower. How much useful TTS fits inside this constraint? The release is interesting. Some tiny TTS announcement count only the acoustic model. They still need a separate learn vocoder to turn acoustic feature into sound. Inflect publish count covers the deployed neural path, text encoding duration prediction, latent speech generation and integrated waveform decoder. Think of it like a compact printer. The text is the document, the middle stage decides timing and pronunciation and the decoder lays down the final audio samples. We don't need to send an intermediate representation to a second neural machine. The English normalization and phoneme frontend is still CPU side code. That code expands and interprets text before the neural model runs. But there is no external learn vocoder or hosted synthesis component required to produce the waveform. This is why complete is a meaningful claim here. Architecturally, this is compact member of VITS family. A transformer encodes the phonemes. A stochastic duration predictor estimates how long sound should last. Monotonic alignment keeps text and audio moving in the same direction. Latent variable generation and residual coupling flows create the speech representation. Finally, the Alice reduced decoder produces the waveform. Micro spends more parameters on hidden and decoder width. Nano narrows the network while preserving the same public contract. Numbers are usually close between the two sizes. Micro reports a 4.395 UTMOS22 predicted naturalness score and 3.99% semantic word error rate. Nano reports 4.386 and 4.21%. On the managed 4 thread CPU test, Micro produced 6.28 seconds of audio per second of wall time. Nano reached 10.72. Those are author published results, but the evaluation artifacts, prompts, ASR output, confidence intervals, and hashes are exposed for inspection. That is better than a single mystery score. Still doesn't flatten these metrics into better voice. UTMOS is a learned predictor, not a human listening panel. Word error measures intelligibility, not word or expression. The useful signal is that Nano does not collapse when the footprint drops to 16 megabytes. There is also community preference evidence. Micro recorded 66p just the voice is official playground. Hosted mode is convenient because nothing downloads to our device. It also let us send the same text, speed, variation and pitch to both models. Micro is positioned as quality first. Nano is footprint first. I'm not going to talk over the comparison. The impulse.
Wait, are you actually being for real? I thought the train left 20 minutes ago. Wait, are you actually being for real? I thought the train left 20 minutes ago.
Important detail is not whether you prefer one sample. It is how small the gap feels compared with 2.35 times difference in a normal footprint. Here is where the claim becomes more interesting. I am switching to browser WebGPU on device. The page says our text and generated audio stay in this tab. There is no server queue or hosted quota. Local run downloads the ONNX model and compiles it on the device. After that, generation happens through WebGPU when available with a WASM CPU fallback. I am starting Nano with a longer sentence containing money, a clock time, a date, and an alphanumeric order number. The page begins with playback after the first sentence and shows each generated word as it progresses. The run completes and exposes a downloadable WAV. This proves the browser local deployment path works. It does not prove any browser or a phone will have the same speed, so we will keep that claim narrow. It is also reveals another footprint detail. The first browser local run has to download an ONNX model and initialize the runtime. 16 megabytes describes a Nano FP32 weights. Not every JavaScript, WebGPU, WSM, phonemizer and browser component around it. Model size and shipped application size are related, but they are not identical. Now we move from a demo page to a reusable local runtime. I am cloning the public Inflect repository and creating an isolated Python environment. Now, one practical warning, use a Python version supported by current Python suite. On Windows 3.11 or 3.12 is the safe recording choice. If your default Python points to a newer unsupported release, the model is not broken. Your package resolver simply cannot find a compatible torch build. And the requirements include PyTorch, Hugging Face, Hub, NumPy, SciPy, SoundFile, the Polymizer, and an eSpeak NG loader. The environment is larger than model weights. That distinction matters when we talk about 16 megabyte model versus the total application package. I am keeping the visual environment visible because reproducibility starts before inference. We want a clean dependency boundary, a known Python version, and command another developer can repeat. For a direct model repository install, Hugging Face also documents its version-aware HF download command, the GitHub example. The repository gives both models one interface. I am starting with Nano. On the first run, the script downloads and catches the selected checkpoint. Then it writes a standard WAV file. Now I change one argument from Nano to Micro. The text output path and a workflow stay the same. Now I change one argument from Nano to Micro. The text output path and a workflow stay the same. Now I change one argument from Nano to Micro. The text output path and a workflow stay the same. Now I change one argument from Nano to Micro. The text output path and a workflow stay the same. Now I change one argument from Nano to Micro. The text output path and a workflow stay the same. Now I change one argument from Nano to Micro.
The complete local voice can fit almost anywhere. The complete local voice can fit almost anywhere.
After the files are cached, I can disconnect the network and run the same command again. A new WAV appears. That is offline claim in the practical sense. Local model files, local text processing, local inference, and local audio output. Under the Python API, both models return 24 kHz monofloat waveform. That makes the output ordinary audio rather than a proprietary playback object. We can write it to disk, stream it through an application layer, or feed it into the same editing and quality control tools we already use. A fair comparison uses identical text and controls. This sentence mixes a name, a rare word, a phrase, and a date. The script renders both outputs into one folder. I am matching listening level before judging. Louder audio often feels better even when it's not pre-done. Micro has more capacity for clarity, stability, and overall quality. Nano is more aggressive about footprint. The right answer is not one use. If Nano is intelligibly enough for your product, the smaller file and faster CPU rate may matter more than a subtle quality gain. Listen again for consonant edges, spacing around the proper names, and the final syllables. Those details often separate an output that is merely understandable from one that can repeat all day without becoming tiring. For a notification voice, Nano may already clear the bar. For narration, Micro's extra capacity has more room to matter.
Professor Nguyen mailed the fluorescent poster to Reykjavik on July 21st. Professor Nguyen mailed the fluorescent poster to Reykjavik on July 21st.
Inflect exposes peaking speed, delivery variation, and a random seed. A fixed seed reproduces the same latent sample on the same runtime stack, which is useful for tests, games, and deterministic content builds. Long text is handled by punctuation-aware segmentation. The front-end breaks passage into manageable chunks, synthesizes each chunk, then joins them with control pauses and edge fades. That bounds memory and makes long passages practical. But it is not one globally planned long-form performance. A transition between the chunks can sound different from a model that plans the whole paragraph at once. That will matter for audiobooks more than short notifications or a dialogue line. Variation is another trade-off. Lower values produce steadier delivery. Higher values give each take more difference, but can also change timing and punctuation. or pronunciations. For benchmark comparison, keep the seed and every control. For creative content, generate several texts and choose by ear. Reproducibility and expressiveness pull in opposite direction. And the API let us decide which one the test Inflect's own documentation warns us about. This sentence combines an unfamiliar name, currency, a date, a city, and abbreviation, a time, and 3 homographs. I am using the same seed for both models. We are listening for punctuation, missing words, clipped endings, metallic artifacts, and awkward pauses. And
Dr. Nguyen paid $12.60 on July 21st. Meanwhile, Ljubljana's AI lab rebooted at 3:07 p.m. after reading SQL, lead, and live in the same paragraph. Dr. Nguyen paid $12.60 on July 21st. Meanwhile, Ljubljana's AI lab rebooted at 3:07 p.m. after reading SQL, lead, and live in the same paragraph.
this is the honest boundary. Inflect can sound surprisingly clear on a normal English, but numbers, abbreviations, uncommon names, and context-sensitive words remain front-end dependent. Nano may also sound thinner, while either model can produce a metallic or a clipped artifact. If your recorded result makes a mistake, leave it in. The value of this model is not perfection. It is the amount of usable speech packed into tiny auditable local system. A useful bug report includes exact text, selected model, seed runtime, and what sounded wrong. The voice is bad is not actionable. Nano seed 7 pronounced Longimla incorrectly after this date string gives the author a reproducible case. That is also how we should test the model in a product. Save difficult prompts as regression pictures and rerun them whenever the model or front-end changes. This sample passed better than I expected, but one clean sentence does not erase the documented failure. The evaluation is more transparent than the average model launch, but the boundaries matter. The naturalness scores comes from a predictor. The intelligibility headline averages two ASR systems. The CPU results comes from a managed 8 vCPU machine with 4 framework threads, fixed prompts, and the first cache building pass excluded. The community preference results is anonymous and randomized, but it is deceptive evidence, not a formal MOS study. So, the benchmark supports a narrow conclusion. These are usually a small complete weights that remain intelligibly and comfortably faster than a real time in the published reference setup. They do not prove that every laptop, browser, phone, accent, and sentence will behave the same way. Competitor charts needs the same discipline. Keaton TTS, Piper, and Supertonic are useful compact baseline, but each occupies a different point in the feature and deployment phase. A fair product decision starts with required capabilities. That Inflict makes sense when footprint, privacy, and deployability matter more than a speaker choice. Think offline game dialog, local assistance, accessibility prototypes, browser utility, device notification, or an embedded app that needs a dependable fixed voice without cloud boost. It is the wrong tool when you need voice cloning, multiple speakers, multilingual output, or premium long-form performance. It is also not validated for a medical, legal, emergency, or accessibility critical communications. For a production architecture, I would wrap the local runtime behind a smaller service or worker cache common phrases in the model version and seed for a test and log the exact text when synthesis fails. For C++ today, owning runtime is the cleaner direction. For Python, the public API is already straightforward. Put a queue in front of synthesis so application threads never block. Warn the model at startup to avoid measuring cache construction as user latency. Return WAV or PCM through a stable interference and fallback to pre-recorded critical phase in generation phase. A tiny model reduces one constraint, it does not remove production engineering. My verdict, Inflect V2 crosses the line from size experiment to useful local component. The complete claim is credible because the published package covers text to waveform inference, including the decoder. The offline claim holds after the files are downloaded. The reference CPU results are comfortably faster than a real time, and the browser local paths makes the deployment usually approachable. The twist is that Nano may be the important release. Micro sounds stronger and is still tiny, but 16 megabytes opens different product doors. Just keep the scope honest. This is one English male voice. It can struggle with difficult normalization and a long form continuity. It is open weight, not a fully published training recipe. Within those limits, Inflect V2 is one of the clearest examples of how much useful speech AI can fit into a truly small package. The public release includes the weight inference and front-end code evaluation from reports and integrity hashes under Apache 2.0. The privacy corpus generation pipeline, filtering infrastructure, and complete optimization recipe are outside of the package. That is enough to audit, deploy, and release system, but not enough to reproduce training end-to-end from raw data. The next test is bigger. Combine an offline speech recognizer, a local language model, and Inflect into one private voice assistant, then measure the total latency on consumer hardware. That is where a tiny TTS model either becomes a system advantage or disappears inside the rest of the stack. That build is the next video.